All right, let's get right into it. Today we are digging into one of the most fundamental jobs in all of computing, search. We're going to look at the brilliant strategies that computers use to find that one specific piece of information in a massive digital haystack. We'll start simple and then get into some really clever stuff.
I mean, just think about it for a second. Every single time you search for something online, a product, a photo, a person, you're kicking off one of these search processes. So how in the world does a system with billions of records find exactly what you're looking for in a fraction of a second? It honestly feels like magic, right? But it's not magic, it's just a masterpiece of algorithmic design.
And here's the secret. There's no single trick. It's more like a whole toolbox filled with different search algorithms. And the real key is knowing which tool to pull out for which job. So today, we're going to build up our understanding starting with the most basic plan and working our way up to the really smart ones.
So our journey starts with the most intuitive strategy you can possibly imagine. When you've lost something and you have no idea where it is, what's the first thing you do? Well, you start at the beginning and you check everything one by one.
This is what we call a linear search. You can picture it like you're looking for a specific page in a book, but the book has no table of contents. Your only option? Start at page 1, flip to page 2, page 3, and just keep going until you find it. That is linear search in a nutshell. It's simple, it's direct, and it's guaranteed to work, eventually.
In the world of computer science, we say this has a time complexity of O of n. Now, that's just a fancy way of saying that the time it takes to find something is directly tied to how many items you have. Got 10 items? It might take up to 10 steps. Got a billion items? Well, it could take a billion steps. So here's the bottom line. It's perfectly fine for small, messy, unsorted lists, but it just does not scale when things get big.
Okay, so how do we get faster? We get organized. As soon as our data is sorted ahead of time, think of a dictionary or an old school phone book, we can unlock some way more powerful and way faster strategies.
And this brings us to the absolutely elegant binary search. Instead of starting at the beginning, you jump straight to the middle of the list. Then you ask one simple question. Is the thing I'm looking for higher or lower than this middle item? And based on that answer, you get to instantly throw away half of the entire list. You just keep repeating that process. Jump to the middle, chop the list in half, over and over, and your search gets smaller exponentially until, bam, you found your target.
And this is where it gets really cool, because you can see just how much more efficient this is. For a tiny list, just 16 items, a linear search might have to look at all 16. But a binary search, it'll find it in 4 checks, maximum. Now, that gap gets absolutely astronomical as the list grows. For a list with a billion items, a linear search could take a billion checks. Binary search, it takes about 30. That is the incredible power of what we call logarithmic complexity.
And hey, binary search isn't the only clever trick in the book. As you can see here, there are other options like jump search, which checks items in fixed blocks or jumps instead of one at a time. Then you've got interpolation search, which makes an educated guess on where an item might be, kind of like how you'd guess a name starting with W is probably going to be near the end of a phone book. They all have their own unique trade-offs, but the main takeaway is this: sorting your data unlocks a whole new universe of high-speed searching.
But what happens if your data isn't in a neat, orderly list? What if it's a big, complex, interconnected web, like a social network or a roadmap, or even the internet itself? For that, we have to start thinking in terms of graphs.
So when we're searching through a graph, we've got 2 main strategies. First up is depth-first search, or DFS. This is like trying to solve a maze. You pick one path and you go as deep as you possibly can until you hit a dead end. Then you backtrack and you try another path. It's awesome for solving puzzles. Then you have breadth-first search, or BFS. This one is more methodical. It explores all of the immediate neighbors first, then their neighbors, spreading out from the start like a ripple in a pond. This is actually how a GPS finds the shortest route. It's guaranteed to find the closest solution first.
And the really cool part is that even though they work so differently, they're both incredibly efficient. Their performance is O of V plus E, which just means their speed scales directly with the size of the graph, the number of vertices, or nodes, plus the number of edges, or connections. So no matter which path they take, they're designed to visit every part of the graph exactly one time, making sure nothing gets missed.
Now, that whole idea in depth-first search of going deep and then backtracking leads us to one of the most powerful and, let's be honest, sometimes mind-bending concepts in all of programming: recursion. It's basically the art of solving a problem by having a function call itself.
At its core, recursion really only has 2 rules. First, you need a recursive case. That's the part where the function calls itself, but with a slightly smaller piece of the problem.
And second, and this is absolutely 100% critical, you need a base case. This is the stop sign. It's the condition that tells the function, okay, the problem is small enough now, here's the final answer, so you can stop calling yourself.
Let's look at a classic example, factorial. To solve factorial 3, the function knows it needs the answer to factorial 2, so it calls itself. That call then asks for the answer to factorial 1, which then asks for factorial 0. Finally, factorial 0 hits our base case, our stop sign, and it just returns the number 1. That answer is then passed back up the chain, solving each little piece of the puzzle on its way out.
Now, this whole process of functions calling other functions, or even calling themselves, it's not magic. There's a very specific mechanism inside the computer's memory that manages all of this. And understanding that is the key to really grasping both the power and the danger of recursion.
That mechanism is called the call stack. The best way to think about it is like a stack of plates. Every time a function gets called, a new plate is placed on top of the stack, holding all the information that function needs to do its job. And the function that's on the very top of the stack, that's the one that's currently running.
So, when our factorial of 3 calls factorial of 2, a new frame for a factorial of 2 gets pushed right onto the top of the stack. Then factorial of 1 gets pushed on top of that, and factorial of 0 on top of that one. The stack just keeps growing deeper and deeper with every single recursive call.
But once the base case, factorial of 0, is finally hit, the whole process reverses. Its frame gets popped off the top of the stack as it returns its value. Now the frame underneath it has the answer it was waiting for, so it can finish its own calculation, and then it gets popped off too. This unwinding keeps happening all the way down until the original call factorial of 3 finally gets the final answer.
So what happens if you forget to put in that base case? What if you forget the stop sign? Well, the function will just keep calling itself and calling itself, pushing more and more frames onto the stack, making it grow deeper and deeper until the computer literally runs out of memory for the stack. And that is the infamous stack overflow error, and it is by far the biggest danger of using recursion. So, as we've seen, from the dead simple linear search to the complex dance of recursion, there's no single best way to search for something. The entire art and science of it really boils down to this simple idea. It is a constant game of trade-offs. Do you need raw speed? Is your data already sorted? How much memory can you afford to use? Choosing the right algorithm is all about understanding your specific problem and the constraints you have to work with.
We have just walked through the fundamental building blocks for how computers find information. And these aren't just abstract theories, right? These are the architectural plans behind the services you use every single day. So the real question is, now that you're armed with these strategies, what kind of complex problem are you going to go out and solve? Thanks for watching.